In this video, we're continuing our discussion of multiple degree of freedom systems. And here we're going to consider the eigenvalue problem. So the problem of finding natural frequencies and mode shapes for multiple degree of freedom systems is essentially an eigenvalue problem. To see this, recall that the equations of motion for a multiple degree of freedom system can be written as our mass matrix times x double dot, which is the vector of our accelerations, plus our stiffness matrix times x, which is the vector of our coordinates, is equal to the zero vector, where m and k are the mass and stiffness matrices, and x is the column vector containing the coordinates. So we look for solutions where all coordinates are undergoing simple simultaneous harmonic motion of the form x is equal to a sine pt plus phi, so that the acceleration is given as x double dot is minus a p squared sine pt plus phi. And when we substitute these into the equations of motion, we get the expression shown here. We can, this has to hold for all time, so we can cancel out the sine pt plus phi, and we're left with this expression, or Ka is equal to p squared ma. If we pre-multiply each side of this by the inverse of the mass matrix, we get this expression here. So m inverse k we can call d, multiplied by our a vector, is equal to p squared m inverse m, which is the identity, times a. So that dA is equal to p squared a. This is the standard form of the eigenvalue problem, where d is equal to m inverse k is known as the dynamic matrix, and p squared are the eigenvalues of d. A are the associated eigenvectors of d. Now, as an aside, let's recall what the standard eigenvalue problem is. So this says that given a matrix M, we seek a non-zero vector v and a real number lambda such that mv is equal to lambda v. So this is equivalent to saying mv minus lambda v is equal to the zero vector. Or m minus lambda I, where I is the identity matrix, times the vector v is equal to the zero vector. So to solve this, either v is equal to the zero vector, which gives us the trivial solution, or m minus lambda I is not invertible. So in that case, the determinant of m minus lambda I is equal to 0. So, and this gives us the characteristic equation of our matrix M. The values of lambda are the eigenvalues, and the associated vectors v are the eigenvectors. So now let's go back to our equation. So we have dA is equal to p squared a. So we can see that this is in the same form as a standard eigenvalue problem, which we can write this as d minus p squared I times a is equal to 0. So the natural frequencies squared, or p squared, are the eigenvalues of d, and the mode shapes a are the associated eigenvectors of d. If we had started with 8.27 and pre-multiplied each side by k inverse instead, we would get this expression here. So we'd had k inverse k, which is the identity matrix, times a on one side is equal to p squared k inverse m times a. So we can call this k inverse m d star. D star, so what we get is d star a is equal to 1 over p squared a. This is another formulation of the standard eigenvalue problem. In this case, the eigenvalues of d star are 1 over p squared. Alternatively, we can, if we start somewhere near 8.27, we can write minus p squared ma plus ka is equal to 0, or k minus p squared ma is equal to 0. And again, we can get the characteristic equation from the determinant of k minus p squared m, as we have seen in the previous sections. With any of these formulations, the eigenvalues give the natural frequencies squared, or p squared, and the eigenvectors give the mode shapes of A.